Hello, this is Jack Jackson. In this video, we're going to talk about the Euclidean geometry transversal to parallel lines theorem. So we have this set up here. This is more technical to get everything set up. But basically, we have this set up here that I'm going to illustrate here. Here's the Euclidean general situation here, where we have a line and another line, two lines, and then a what's called a transversal that intersects in 2 points. Okay, just reviewing real quickly what we did last video, we saw that these lines give us uh, 8 angles here, 8 proper angles, 4 here, 4 here. But because vertical angles are congruent, that's at most 4 different sizes. But it's possible, we saw that if we get these to be parallel, then we actually it boils down to just 2, or of course if they're right angles, only 1. Angle size. So we have basically 2 angle sizes here. All the red ones, the odd labels here, are congruent, and all the blue ones are uh, are congruent to each other. And if take any red and any blue, any odd and any even labels, then they turn out to be supplementary. So we had a couple of things. We had the Z property here, that if we have a pair of alternate interior angles congruent, then we have to get this parallel set up, and we get the 2 sizes of angles. Another way we looked at was the F property. See the letter F? So a corresponding angle like 4 and 8, if they're congruent, then we're in this situation where we have parallel lines. And then we had the C property. If we have, here's kind of see a stylized letter C there. 2 angles on the same side of the transversal that are interior. If they're the same, not the same measure, but supplementary, then the 2 lines, the original lines, had to be parallel. Okay, and it turned out, if we remember, that this works in hyperbolic as well, that if you get, say, uh, the alternate interior angles congruent, then you have to have parallel lines. But we also saw that there are many, many more parallel lines in through that same point, infinitely many in fact, and only one of them has the correct size of angle there. So the converse is not true in hyperbolic geometry. So the straightaway first version is Z property says if you have a pair of congruent alternate interior angles congruent, then these 2 lines have to be parallel. And we'll see in Euclidean geometry that if you've got the parallel lines, the alternate interiors have to be congruent, but that second version, where you start with the parallel lines, does not necessarily make them congruent in hyperbolic geometry. Okay, so how do we basically prove this? Let's go over the proof of the first part. So we did it by contradiction. So pretend, if you can't really do it, but pretend A3 and A5 are congruent. Then if these lines are not parallel, they intersect at some point P. We've got a triangle. A5 is an exterior angle to this triangle, and A3 is a remote interior angle. Our theorem says that this angle must be strictly greater in measure to that, and it's not. It's the same. I mean, of course, it actually is here, but if this were congruent, we have a contradiction. Therefore, the only way we have is a parallel line. Okay, now we're going to prove the converse of that. So if we start with parallel lines, what can we say? Well, basically what we do here is we take a line through here, through X, and we say, hey, wait a minute, we can make this angle y, x, whatever this is, r. We can make y, x, r any size we want, right? We can go anywhere from 0 there, to pi if we go around. Well, let's make it the same. Let's pretend that's the same angle there as this angle here. So construct it that way. Well, wait a minute. What does that tell us? Okay, by the z property the other way that we've already proved, if we have a pair of alternate interior angles that are congruent, then this has to be parallel. Well, wait a minute, what do we know about Euclidean geometry? There is only one parallel line through x parallel to this line down here. So, in fact, this line r, xr, has to be the same as the original line AB. It has to be up here on this line because why? Because there's only one parallel. So that's an unusual situation. We were able to use the converse of what we were trying to prove to help us prove the thing we were trying to prove, right? So in other words, we use the fact that a pair of alternate interior angles that are congruent must make the lines parallel. We use that to help prove the converse, that if we have a pair of parallel lines, then alternate interior angles have to be congruent. So, yeah, so interesting setup there. Okay. Now, really, once you prove that, then we've got everything else in this entire proof, because once you know, we've already proved that if you've got a pair of alternate interior angles that are congruent, then all pairs of alternate interior angles are congruent. All pairs of corresponding angles are congruent. All pairs of in exterior angles, alternate exterior angles are congruent. All pairs of interior angles on the same side of the transversal are supplementary, and so forth. And so those are all if and only if situations. So once we prove the z property in both directions, we have the c property in both directions. That is, if you a pair of lines are parallel, if and only if uh, they're parallel, if and only if you have a pair of alternate or interior angles on the same side of the transversal are supplementary, the c property. Uh, we have the f property. A pair of corresponding angles are congruent if and only if the lines are parallel. Again, the if and only if works in Euclidean geometry, and it works in one direction in all of these work in one direction in uh, hyperbolic geometry, but not in the other. But they work in both directions in Euclidean geometry. Okay, so this is a very, very important result. And so why are these two videos about parallel lines in my playlist on quadrilaterals? Well, the next thing we're going to do is start looking at quadrilaterals with at least one pair of parallel sides, trapezoids and subclasses of trapezoids like parallelograms. And in the process of doing these proofs about parallelograms, or trapezoids, we're going to use one or more of, say, the z property, or the c property, or the f property, or one of these other properties of this parts of this transversal to parallel lines theorem. And if we're trying to keep track of hyperbolic geometry, we'll have to be careful which way we're going with these, and we'll see that under, if we have it set up where we're going in the correct direction, where we have the congruent angles or supplementary angle pairs that we need, then we can turn around and get the conclusion that the lines or the sides of the quadrilateral are parallel. Whereas if we're going the other direction, well, if you start with parallel, we're only going to get the result about, say, the C property or the Z property. We're only going to get that in Euclidean geometry, but not hyperbolic geometry. I'm just going to go right, here's the actual proof written out, just in case anyone wants to pause the video and write it down. So there it is, there's part of it, and there's the rest. So during this week, we're going to formally investigate the question about the sum of the measures of the interior angles of a triangle, the number of parallel lines to a given line through a given point. And it turns out the different conclusions of these two questions, different conclusion, one for each of the three geometries, are actually equivalent. And so, for example, if there's a unique parallel line to a given line through a given point not a line, this is logically equivalent to knowing the sum of the angle measures of the interior angles is always equal to pi, or 180 degrees. Since all hyperbolic, spherical, and Euclidean geometries all have different conclusions about the number of lines parallel to a given line through a point not a line, we'll need additional postulate, the Euclidean parallel postulate, If we want a narrow focus to Euclidean geometry, discover this fact is one of the most interesting and profound mathematical discoveries in the history of mathematics. And then here's some different things here. Let's take a quick look at these. So if you go to my geometry collector resources and go to parallel lines, this is my transversals to parallel lines thing that we've done. And here are some other things that are related to it. So this, for example, here is showing you that when you have the parallel lines, that the alternate interiors are congruent. There's the other pair, parallel lines, alternate interiors are congruent. These are same size, same side of the transversal. Notice here, we can see the supplementary going. We're going to basically pull this guy up to its corresponding angle and see that they're supplementary. Here's the other pair. Interior angles on the same side of the transversal are, if they are supplementary, then you get parallel. That works in hyperbolic as well, but it's an if and only if here for Euclidean. Here is alternate exterior angles. So those two are congruent, that one and that one. Here's the other pair, that one and that one. Okay, so those are congruent. Here's where we have exterior angles on the same side of the transversal. Once again, those are supplementary. Here's the other pair on the other side. Again, supplementary. You can kind of see that now. Let's see, what do we got here? Here's showing some angles to look at. So there's your vertical angle pair. This one here, we can rotate it around. That's the vertical angles that are there. So it's showing you some vertical angles. Here's another one here. This one. This is showing you corresponding ones. And there's alternate interior one there. Congruent. Here's one where we're looking. Let's see, we're looking here. Corresponding there. Corresponding there. Corresponding there, and so forth. Nice little applet there. Here's one with supplementary pairs. These two are supplementary. If you go, those two are going to still supplementary. This one here and this one are supplementary. We can go here, right, and see some supplementary pairs there. Here's another activity showing same side interior angles. Here you can see the relationship is that they're supplementary. This one here is showing exterior angles, okay, that they're congruent. Alternate interiors, they're measured here so you can see they're congruent. Of course, it's dynamic. You can move these around and show that even though the angles are changing, they're the same size as each other. Here are the corresponding ones here. Here's another pair of corresponding ones. Third pair here. Fourth pair here. Notice that every time they are congruent. There's the F property there. So here your F is kind of, let's see, is backwards, but it's still the F property. F property. Okay, upside down F there, F property. This is a Z property. That, upside down Z here. Okay. Alternate exterior, I don't have a letter for that one, but there they are. Same size interior, that's the C property. They're supplementary. Now your C's backwards. Same side exterior, don't have a letter for that one, but there it is. And this is another one that you can look at if you want. Okay, so we've seen a lot of things about transversals to parallel lines. Okay.